Hi, today we're going to look at some properties of definite integrals. And to start with, I'd like you to calculate these four definite integrals. So please pause the video and have a go at that. Okay, and hopefully you've read the fifth question. What is going on? So I'm just going to quickly, I'm just going to show you the answers, and then I'm going to go through one of them. If you didn't know where to start, if you have got all the answers correct, then you can sort of skip on a little bit. But if you haven't, or you didn't know what to do, then just remember. So we take the integral and we put square brackets, and then we integrate each of the functions. So 2x becomes x squared becomes a third x cubed. We close the square bracket, and then we put our limits in, and then we substitute these in. We substitute the higher one in, so we're going to get 2 squared, which is 4, minus 1/3 times 8, okay, because that's 2 cubed. And we're going to minus when I substitute 0 in, but in this case, that's just going to give me 0. So that's going to then give me 4 minus 8 over 3, which I could write as 12 over 3 minus 8 over 3 if I'm keeping it non-calculator, and that's going to be 4 over 3. The others are going to work in a similar way, but look what happens. If we integrate from 0 to 2, we get 4 over 3. If we integrate between 0 and 3, suddenly we get 0. So how can we have an area and then it suddenly disappear? If we integrate between 0 and 4, we get a negative. And then I also asked you to integrate between 2 and 4, and we also get a negative here. That might be a bit of a hint if you didn't get it from here. What is going on? Basically, previously we spoke about how we can integrate and find definite integrals and work out areas under curves. We did this, we've improved why it works, and then we looked at some examples, including ones where you have to sketch the graph as well. Okay, why don't we sketch this graph? That might help us figure out what's going on. So I'm just going to leave enough, get rid of this, so I've got enough space. So if I want to sketch y equals 2x minus x squared, I can factorize out the x. That gives me my roots of 0 and 2. I know it's a negative quadratic. It's going to go up like so. And this is starting to make a bit more sense. So the first integral was this, because we had 0 and we had 2. When I integrated between 0 and 3, this is the area that I would have found, but I'm not finding an area. What I'm finding is this positive 4 over 3, and then this thing is actually a negative. I don't want to say it's a negative area, but it's a negative value that I get out of it. So this must be the integral between 2 and 3 must be minus 4 over 3 for it to cancel out, basically. Okay, so I'm going to write minus 4 over 3. And then if I carried it on to 4, then that's when the negative takes over. Okay, so you can see, hopefully that makes sense what's going on. We are finding positive answers to our integrals, but we are also finding these negative answers to our integrals. And if we integrate between a region where the graph is positive and negative, then you actually add them together. So this 4, 0, okay, is equal to my integral between 0 and 2 plus, I mean, I've not included everything here, plus my integral between 2 and 4. Yeah, 4 over 3 plus minus 20 over 3 equals minus 16 over 3. Just to summarize, be careful when defining a definite integral as an area. It's not quite that. There's areas going on, but we need to incorporate this negative aspect. If we go underneath the curve, we get a negative answer. Secondly, some properties of integrals. If you integrate between a and b, and c is in between, then you can integrate between b and c. Sorry, I've done this the wrong way around. If you want to go between a and c, then you can go from a to b and then b to c. That's essentially the general formula for what I just did here. I said that the integral between 0 and 4 is the integral from 0 to 2 plus the integral from 2 to 4. You can always do that. Now, it won't give you areas as such because of this issue, but this is a fact. And I've asked you to have a go at proving this on a problem sheet. One other one is that if you have an integral and you flip the signs round. Before, we've always had b as the larger number, but there's no reason why you have to do that actually. So, and there are reasons why sometimes you might not want it to be. You can actually flip it around and then make it negative. Now we're going to prove this one. So how do we prove it? We're going to let di by dx equal f of x. Why have I done that? Because I'm saying I want to integrate f. I'm saying the derivative of I is equal to f. So that means that the integral of f is going to be I x. I is a new function. We would add c to it, but because we're going to be doing definite integrals, I'm not going to do that right now. But what we are going to find if we okay, I just need to move this example. If I want to work out this thing here, then on the left, the answer is going to be, when I integrate f of x, I'm going to get I. But I know that I then put my limits in. So I'm going to get I x, and then I'm going to substitute my limits in. And then I would get I b minus I of a. Now I could choose to write that as, bring out the minus and make it minus IA minus IB. See what I've done there? I've just factorized that a minus. I can do that, there's nothing stopping me. But this thing here is equal to this. It's minus my integral of f of x. So I've proven it. Okay, proof complete. That property is true. And you can use a similar reasoning to prove this one up here, but I'll leave you to try that. We're going to carry on with two examples using this new knowledge. It's finding areas under curves, but we need to be careful when there's negatives. So example 1, find the total area of the finite regions bounded by the curve y equals 2x minus x squared, the x-axis, and the line x equals 4. Okay, I've chosen this example because this is essentially what we've just been talking about. So here, sorry, I just need to move this second example out of the way. Okay, this graph is illustrating y equals 2x minus x squared, the same. I spoke for it before about factorizing it, finding the roots, and then drawing it. So, find the total area. That's going to be this blue bit, and then I'm going to be adding on all of this. Now, let's just cross out this bit. We weren't interested in that. So what I'm going to need to do is I'm going to need to do the integral of 2x minus x squared dx between 2 and 0. That's going to give me my positive area here, and that's going to equal 4 over 3. What I'm then going to have to do separately is do the integral from 2 to 4 of this same function. And again, you worked out that one in the starter. That was equal to minus 20 over 3. Now that is the integral, so the area itself, we just need to change the negative. It's going to be, so the area is going to be 20 over 3 for this bit here, this region here. And finally, total area is going to equal 4 over 3 plus 20 over 3. So I can still find areas as long as I'm careful. I really need a sketch to help me out. Then I'd get 24 over 3, or simply 8. And that's how we can do it. So another way we could have done it would be to have done it directly, but recognize that this bit's positive, and then I would subtract the negative area here, and that would have also worked out to give us the answer that we needed. Okay, one more example. So we've understood area. We can calculate areas using definite integrals. Be careful with negatives. We've done it for a quadratic where we've sketched it and calculated the area separately. We are now just going to do the same for a cubic. So sketch the curve. That is going to allow us to find the area, because we know where the roots are, but we need to be careful about which bits are positive area and which bits is this sort of negative area. Okay, let's sketch the curve. We know the roots are going to be 2, 0, and minus 1. I can just write those straight down. I'm going to draw my axes, and then I'm going to plot where it goes through 0, 2, and minus 1. I know the leading power is going to be x cubed, so it's going to be a positive cubic. It's going to look a bit like this. So I can draw it as such. There we go. Okay, and what I'm interested in is these areas here. So we've got minus 1, 2 here. So what we want is let's go for it. The total area is going to be the integral from minus 1 to 0 of x minus 2, x plus 1 with respect to x. And then because this bit's going to be negative, I'm going to minus from 2 to 0, same thing. Okay, if you want to be a bit more careful, then just work these two out separately, and then just flip the negative sign on the second one. It'll work out to be the same thing. And to be honest, that is probably a bit more careful. Maybe I'm just being a bit reckless here. Okay, so we just need to expand this. So we're going to get x squared minus x minus 2. I've done that quite quickly. I've added these two numbers, give me minus 1, give me that, and then I've multiplied them to give me the minus 2, and then I can multiply it out again. And while I'm at it, just away from the main integrals, I might want to integrate that. Now, when we deal with cubics, like you either have to make the cubic quite horrible to give you nice answers, say have like, to get integer answers, you're going to have things like 4x cubed, so when you integrate it you get x to the 4. Otherwise you're always going to get fractions. So these questions are likely to be nice to factorize, but they're going to give fractional answers. Okay, we will get that here. So when I integrate it, I'm going to get 1 over 4 x to the 4 minus 1/3 x cubed minus x squared. Of course, I've got a plus c as well, but I'm about to incorporate it into the definite integral. So it's going to sort of move that just a bit below. Okay, I've changed my mind actually. I'm gonna find area 1 and I'm gonna find area 2. So area 1 is this, and area 2 is this second one. So if I want area 1, it's going to be brackets, and then I've got my result from before, close brackets, 0 minus 1. I'm going to substitute in for that. When I put 0 in, I'm going to get 0, and I'm going to minus a quarter. That's going to become minus 1. It's going to get plus a third, and then I'm going to minus 1. Okay, do be careful with this. And that's going to give me minus, I probably would get my calculator at this point just to be safe, minus 5 over 12 or 5 over 12. So I have found the first area, which is 5 over 12. Now I'm going to find the second area. I'm going to delete that now. Okay, the second area is going to be, I've already done the integral, it's the same function I'm integrating. But now I'm integrating between 2 and 0. I'm going to substitute in. I'm going to get 2 to the power 4, that's 16, divided by 4 is 4. I'm going to minus 8 over 3. Then I'm going to minus 4. And then I'm going to minus 0. And I'm going to get 8 over 3 minus 8 over 3 is my final answer. Okay, we're nearly there, because that means the area is going to equal 8 over 3, and my total area will equal 5 over 12 plus 8 over 3, which is 37 over 12. Okay, and that's it. So this is an extension to definite integration, being careful with negative areas, using properties that we've learned. And yeah, it's important to be able to see, this is why it's so important to be able to factorize, be able to sketch graphs, because this is the sort of thing that you need to be able to do. Okay, brilliant. Thank you.